The moon has always been an object of fascination for mankind. It's a prominent view in our night sky, a moon massive and close enough that its beautiful and eerie details are visible with the naked eye. Mankind stepped on the moon over 5 decades ago, but to this day, there's still so much we don't know about it, as exploring any place outside of Earth is always incredibly dangerous and difficult. While the moon seems like a very different place from Earth, there's one thing that excites scientists about future colonization prospects. There is increasing evidence of water on the moon. But lunar water is mysterious. It does not always show up where we expect it, and by all accounts, it shouldn't be where we find it. Its mysteries are ones that the nations around the world are desperate to crack, because lunar water is the key that might unlock the solar system to us. Whoever solves it first will reap significant benefits. Where can we find lunar water? How do we know it's there? And how close are we to overcoming the moon's greatest dangers to get it? I'm Jon McColgan and you're watching Astrum. Join with me today as we follow the progress numerous space agencies around the world have made to find out once and for all whether the moon's surface contains water. Scientists did not always know that there was water on the moon. Lunar 24 was an ambitious robotic probe of the Soviet Union in 1976. It successfully landed on the moon, drilled into the lunar surface about 2 meters deep, and sent about 170 grams of lunar soil samples back to Earth. Of greatest surprise to the scientists was the detection of water within the return sample. Around 0.1% of the sample was water, and they found that the concentration of water increased with depth. However, like the very trace amounts of water detected in samples obtained during earlier moon missions, for example Apollo 11, this was assumed to be a contamination from Earth. The question whether there is water on the moon remained unanswered. In 1994, NASA's Clementine mission showed that permanently shadowed areas that haven't received any sunlight in billions of years do exist near the moon's south pole. As a result of this, there was a lot of excitement in the science community about whether there could be frozen ice at the bottom of these craters, protected from the harsh rays of the sun, where the temperatures would never rise above about -173 degrees Celsius. Any water ice at the bottom of these craters could probably exist indefinitely at these temperatures. Excited by this discovery, NASA launched the Lunar Prospector spacecraft shortly afterwards in 1998, specifically to hunt for clues that water may exist there. While it didn't give us any conclusive answers to the mystery, it certainly added to the intrigue. The Lunar Prospector detected large amounts of hydrogen at the moon's poles using spectroscopy from orbit. Data from Prospector suggested that there could be somewhere between 10 to 300 million tons of water ice scattered inside craters around the lunar poles. But large amounts of hydrogen do not necessarily mean the presence of water. It could also be water's closest chemical relative, hydroxyl. The Prospector spacecraft subsequently crashed into the moon's south pole in 1999, with NASA scientists hoping the impact would blast ejecta into space, lit up by the sun, so that scientists could use spectroscopy to prove the existence of water in the dark craters of the moon using Earth-based telescopes. Unfortunately, no water ice was detected from the Lunar Prospector's impact. The mystery continued. Japan's Selene, or Kaguya spacecraft, was launched in 2007, and its mission was to take high-resolution images of the moon and map the lunar surface. But it also wasn't able to detect signs of water ice in permanently shadowed craters around the south pole of the moon. So, after 18 months of orbiting, it too purposefully crashed into the moon, hoping that this time it would release enough ejecta into space for Earth-based observatories to work with. But again, no evidence for water was found. In 2008, India's first moon mission, Chandrayaan-1, was launched. Chandrayaan-1 was different from previous missions in that instead of relying on sensors to detect water from a distance, India included an impactor that could specifically detect water in its gaseous form through spectroscopy as it came in close proximity to the spacecraft. Scientists believed water vapor could be in the extremely tenuous atmosphere of the moon just above these craters. The impactor probe was released from the main body of the spacecraft and descended for 25 minutes before it crashed near a crater at the south pole of the moon. As it descended, it sent the data back to the Chandrayaan-1 mothership, and within that data was the answer scientists had been looking for all these decades: a confirmation of water. And a few months later, the Moon Mineralogy Mapper instrument aboard Chandrayaan-1, using spectroscopy from orbit, also detected the presence of water on the moon. But NASA wanted more proof. They launched their own Lunar Crater Observation and Sensing Satellite mission, as well as the LRO, an orbiter you will be very familiar with if you follow this channel. LCROSS was a simple, low-cost, fast-track mission, and it had one main objective, which was to once and for all confirm the presence or absence of water ice in a permanently shadowed crater near a lunar polar region. It had a simple, straightforward, yet very clever design. In an unusual move, the first stage of the Atlas V rocket LCROSS was launched from stayed attached to the spacecraft, and upon reaching the moon, it was released to crash into one of the dark craters at the south pole of the moon. This impact was similar to how Lunar Prospector and Japan's Kaguya probes crashed into the moon to eject a debris plume that rose above the lunar surface. But unlike them, the LCROSS spacecraft itself flew through the debris and collected data without relying on Earth-based observatories, which clearly weren't very reliable for studying small plumes of debris. As the debris cloud rose above the crater's rim, it was exposed to sunlight, and any water ice and other molecules of interest were vaporized and broken down into their basic components, which the sensors on board LCROSS were able to detect, only for it to crash into the moon too after accomplishing its task. This combination of collisions produced a large plume of surface material, which the LRO was left to study. As LRO traveled over the lunar surface, it began to notice something unexpected. Trace amounts of water molecules could be found over the top of the surface regolith, the grey rock that makes up much of the moon. It turns out the whole moon is ever so slightly wet. This wetness was even observed to move around in a sort of lunar water cycle, both by region and by time of day. Around noon, when the moon's surface was hottest, the water seemed to dissipate, but then would return with the evening. Nowadays, a staggering 600 billion kilograms of water ice is estimated to be on our moon, roughly the same weight as 461 million cars. That's a lot of water. But how could such water be found on the moon, particularly as ice? Wouldn't it have evaporated out of space, particularly under the hot daytime temperatures? NASA's Lunar Reconnaissance mission recorded surface temperatures as high as 127 degrees Celsius on parts of the moon in direct sunlight. So, something is either generating the water, or something must be trapping it there. There are several hypotheses as to why this might be happening. Micrometeorites raining down on the lunar surface, carrying small amounts of water, could deposit the water on the lunar surface upon impact. Another possibility is that a two-step process whereby the sun's solar wind delivers hydrogen to the surface and causes a chemical reaction with oxygen-bearing minerals in the soil to create hydroxyl. Meanwhile, the bombardment of micrometeorites could be transforming that hydroxyl into water. It could then be trapped into tiny bead-like structures in the soil that form out of the high heat created by micrometeorite impacts. Or the water could be hidden between the grains of lunar soil and sheltered from sunlight. The LRO's observation means that the locations on the moon that might be viable for a lunar base is suddenly much wider. If this trace amount of water could be collected, you would not need to build your base next to a permanently shadowed region, which is convenient because PSRs are far colder than we at first thought. The moon has very little axial tilt. a little over a single degree. This means that at the poles, there exist craters that are never pointed directly at the sun. No matter what time of day or year, the sun never casts light into their mysterious basins. Naturally, a location that never sees any sunlight is bound to be cold. However, scientists were not prepared for exactly how cold it turned out these regions were. For context, at the equator, temperatures on the moon fluctuate between 120 degrees Celsius during the day and minus 130 degrees Celsius during the night. LRO houses a diviner instrument, which uses 7 thermal infrared channels to measure surface temperatures. With it, LRO found a polar crater that had temperatures as low as minus 250 degrees Celsius, making it the coldest temperature measured on any object in the entire solar system. That's colder than the average temperatures of Uranus, Neptune, or even Pluto. The crater edges shielding these areas from solar radiation might have created the perfect storage location for housing water ice, but other more interesting, useful compounds could be found there too. Carbon dioxide, carbon monoxide, dinitrogen, and argon perhaps. Furthermore, NASA's SOFIA, or Stratospheric Observatory for Infrared Astronomy, discovered water on the sunlit surface of the moon, confirming that water on the moon may not just be limited to cold and shadowed places, but distributed across the lunar surface. SOFIA found that the Clavius crater, one of the largest craters visible from Earth, has water in concentrations of 100 to 412 parts per million. To put that into perspective, the Sahara Desert has 100 times the amount of water than what SOFIA detected in the lunar soil. So yes, that is an astonishingly low quantity, and it might not be of much use to us, but it helps us in learning about the lunar surface and how it works. Water is known as the oil of space, and finding a successful, affordable way to mine it on the moon could be game-changing in the space industry. It can be recycled inside a lunar habitat and used for drinking water or washing. It could also be used to help plants grow on the moon, which are needed to nourish future lunar colonists. But the biggest and most immediate application for lunar water is making rocket propellant. Hydrogen and oxygen are 2 of the biggest materials that are used to power rockets right now. You see, getting stuff into space from Earth is a very fuel-intensive and expensive process. And the deeper into space you want to go, the more fuel you need, and the more fuel you have to carry. Having to bring all this from Earth heavily limits space exploration. But the moon has 1/6 of the Earth's gravity. So if we are able to successfully produce rocket propellant on the moon, it's less resource intensive, and transporting propellant from the moon to other locations in space would be nowhere near as expensive as transporting it from Earth. And actually, getting something from the moon to low Earth orbit is less resource intensive than sending it from Earth itself, even though that adds 300,000 kilometers to the journey. So the presence of water on the moon could help make space missions more affordable and dramatically increase our capabilities of exploring the solar system. China, in collaboration with Russia and other countries, is planning to send 3 missions by 2029 called Chang'e 6, 7 and 8, which will be targeting the South Pole, where they plan to establish by 2030 a robotic station. The US also plans to have a lunar base by 2030 on the lunar South Pole with NASA's Artemis program. They plan on launching their first non-manned flight test Artemis 1, followed by a crewed flight test Artemis 2, and finally launch Artemis 3, which will happen no earlier than 2025, and that may be our first manned mission to the moon since 1972. All in all, on the moon, the real estate market is skyrocketing. While I'm being a little tongue-in-cheek when I say that, it is evident that interest in the moon as a permanent base for human life is increasing. Before December 2022, the number of countries and political unions that had successfully sent probes either to orbit or land on the moon has risen to 6. America, Russia, Japan, Europe, China, and India have all sent spacecraft to our closest lunar neighbour. As more countries and companies set their sights on space, it may make you wonder, what's the end goal? Do we simply want to be a spacefaring species? Exploring the solar system for the betterment of humanity? Or do people smell profit in space? While researching this video, I found out a lot of eye-opening reasons why mining in space, and especially on our moon, might well be something that we see happening in the next couple of decades. Why? Well, just wait until you find out what's actually there to be mined. The first substance is known as helium-3. You may have heard of helium-3 in sci-fi stories, as theories suggest it is the ideal substance for a clean type of nuclear reactor, with no radiation and no dangerous byproduct. It also has uses in medicine and radiation detectors. However, it is really rare on Earth. It does occur naturally and can be found in deposits of natural gas, for instance, but it's generally not viable to extract, as even in natural gas, there are only around 100 parts per billion. So let's say we had 1 billion cubic meters of natural gas, you'd only be able to extract around 15 kilograms of helium-3 from it. A lot of the time, that's not economically viable. We can also produce helium-3 as a byproduct of the radioactive decay of tritium. The problem with that, though, is that tritium is a crucial component of nuclear weapons. And so when the world slowed down the production of nuclear weapons, helium-3 stockpiles also started to diminish. Assuming we don't want more tritium in the world, it means we need to find another source of helium-3, especially if technology improves enough for helium-3 reactors to become a reality. Fortunately, we have a world in orbit around Earth right now, which has been bombarded by helium-3 for billions of years, thanks to the Sun. Earth's magnetic field deflects helium-3 traveling with the solar wind around the planet, whereas the Moon, with no magnetic field for protection, simply absorbs it in the top layer of the ground. We aren't talking huge quantities, it has at most 50 parts per billion, but because it's all over the Moon, not just in tiny pockets, it can be collected alongside any other mining operation. It could also be used to power reactors on the Moon itself, which would help a moon base be self-sufficient. Some people think that helium-3 mining on the Moon will not be viable. However, China states that eventually mining helium-3 is one of the primary goals of their Chinese lunar exploration program. American, European, and Indian scientists have all stated it is something they will consider further, and Russia is conducting a feasibility study on this right now. Even private companies are eyeing up the possibility. Because the parts per billion of helium-3 are relatively low, even in the Moon's regolith, it would make sense that whoever was mining for helium-3 would also be mining for something else in the regolith at the same time. But what else can be found in it? As it happens, the lunar regolith is packed with different materials. Look at this false color mosaic of the Moon, each color indicating different deposits of minerals found on the lunar surface. There are plenty of metals to be found on the Moon in large quantities, like iron, titanium, aluminium, silicon, calcium, and magnesium. Some of these metals are locked into hard-to-access minerals and oxides. However, separating the metals will often also produce useful byproducts like oxygen and hydrogen. They are super basic and not rare on Earth at all, but unlocking these elements on the Moon itself will allow for a colony to be self-sustaining, as oxygen means breathable air, hydrogen can be converted to fuel, and combining the two will produce water. Unprocessed regolith could also prove useful, as it could potentially be turned into lunarcrete, useful for building infrastructure on the Moon without having to transport the materials from Earth. Glass could also easily be produced from lunar regolith. And while it's not super ideal, some plants can grow in lunar regolith, helping any lunar base to be self-sufficient in growing its own food, short of using hydroponics. But perhaps the most important resource found on the Moon are, ironically enough, metals known as rare earths. Interestingly, rare earths, which consist of this section of the periodic table, are not actually super rare on Earth. However, the difficulty in mining them is that they have not really collected into big deposits. Rather, they are dispersed through the Earth's crust. This means that they are exceptionally hard to mine on Earth, and there are only a few countries worldwide that have deposits large enough to do anything about it. Even then, most countries don't bother at all because of the massive environmental and human damages that come from the pollution of mining them. The only country that did not waver from these problems is China, as China has around 30% of the planet's rare earth supply. And because it is one of the only countries mining for them, they have a 95% control of the market, which puts China in a powerful position worldwide, especially seeing as these minerals are so valuable to our society, being components of various electronics and batteries. Are countries with somewhat sizable deposits like the US, Canada, Australia, and South Africa going to start digging up their backyard to extract them? Or rather than pollute the Earth further in our attempt to go green, is it actually more feasible to get these rare earths off the moon instead? Rare earths aren't any more common on the moon than on Earth. However, some deposits have already been identified, and pollution on the moon would certainly not have any of the devastating environmental and human consequences attached to doing it here. As demand for these elements inevitably goes up in the coming decades, it could well be that mining for them on the moon becomes economically viable. And not only that, but a control on the market means control of the market price, and whichever country is in control will have a tremendous advantage. Will it be China maintaining their position, or will some of the other spacefaring countries and companies want a piece of the pie? Only time will tell. Which leads on to another curious question. Who actually has mining rights on the moon? Well, it's a bit unclear. The main space treaty, which most countries in the world have signed up to, is called the Outer Space Treaty, and covers things like disallowing weapons of mass destruction in space, disallowing military bases in space, and disallowing claiming any celestial body. However, it doesn't really cover mining. Other treaties have been put forward which would cover mining in space, but so far only non-spacefaring countries have signed up for it. Right now, it could just be a matter of first come, first served. This makes mapping the moon's surface and finding sources of usable lunar water all the more vital. If we intend to colonize the moon, utilizing this water will be incredibly important. However, collecting this water ice might be more challenging than you'd think. And I don't just mean the cold. There are bigger problems we'd have to face if we want to collect and use water ice and other resources from the poles. One of them is electricity. Because of the moon's low inclination, solar winds, mainly made of ions and electrons, pass by the polar regions and the terminator almost horizontally, hitting the crater's leeward. Once there, the negatively charged electrons, which are 1,000 times lighter than the positively charged ions, rush down into the crater's inside walls and bottom, causing these surfaces to become negatively charged. As the electrons rush down before the ions, a difference in charge is formed, causing an electric field to form. A negative charge is created at the bottom and inside walls of the crater, while a positive charge forms above until the positively charged ions are driven into this electric field by the electrons. As you can imagine, the most prominent separation between the two occurs at the crater's leeward, where the solar wind hits. This division between electrons and ions will eventually hit a critical level. Because of this effect, these areas could be charged up to hundreds of thousands of volts, which would have deadly consequences for an unwary explorer. But even if you avoid the poles, that might not be the end of the electrical problems you could encounter on the moon. Another occurs when combined with the fine surface dust of the moon, regolith. The moon has no magnetosphere, so any incoming solar wind directly hits its surface, causing the surface to become negatively charged, and the covering fine dust on the moon, regolith, becomes electrostatic. Regolith is a fine dust with sharp edges which can have abrasive effects. In fact, during the Apollo missions, it was reported that regolith would stick to everything due to its electrostatic charge. This could potentially damage spacesuits and instruments, which would be a huge problem. On top of that, regolith also causes some negative effects on health, causing red eyeness and cough, as it can be highly toxic. Spacesuits in the Apollo missions were made of a material called woven Teflon, which attracted the electrostatic regolith and trapped it into its material. Woven Teflon can also cause a triboelectric effect, making the astronauts a medium between the negatively charged ground of the moon and the positively charged solar wind flowing above their head. This is similar to what happens when you rub your feet on a carpet and then touch the metal handle of a door, causing you to get a small electric shock. A laboratory experiment has even proved that woven Teflon, covered in a simulant regolith, was more prone to an electric arcing. Lunar exploration would be much less appealing if you were constantly getting electrically shocked. So, if the dust and the woven Teflon made the astronauts so susceptible to getting electrocuted, why haven't we noticed before? Wouldn't it have happened during the Apollo missions? Well, this static effect can be offset when photons emitted from the sun kick off some of the electrons from the ground in a process known as photoelectric emission. This causes the ground in direct sunlight to be more positively charged and balance the negative charges brought by the solar wind. Because landers of the Apollo missions landed on a part of the moon which was constantly hit by sunlight, our astronauts had very low chances of getting electrocuted. But that's not to say it wouldn't be an issue elsewhere. So how can we keep our astronauts safe from extreme temperatures, toxic dust that could potentially contaminate moon bases, and the high chances of astronauts getting electrocuted by up to hundreds of thousands of volts of electricity? To avoid that, we would need to design a new spacesuit with dissipative properties that would never allow potentially dangerous electric charges to damage them or cause harm to the astronauts wearing them. You might think a good insulating material is rubber, and you would be right, but this would have to be balanced against the extreme temperature fluctuations these suits would have to face. After all, what would happen to rubber in an environment where temperatures could potentially reach minus 247 degrees Celsius? There are multiple undergoing projects though that are working on finding a solution to these and other problems, but so far nothing definitive has come of it yet. To avoid regolith, a team at the Washington State University was granted $130,000 by NASA on a project involving liquid nitrogen, which has properties that allow it to capture dust like regolith from surfaces, allowing lunar bases to be kept cleaner and avoid risks of getting it contaminated. NASA is also working on a technology involving electrodynamic dust shields, consisting of electrically charged panels which, through wires, shoot currents able to wipe away the regolith from surfaces. A pretty cool way of cleaning. There is also a revolutionary new technology being developed by Intention, a Norwegian tech company which is working on a project called ASG. This technology could potentially enable remote human explorations and missions by using a human-machine interface, which allows people to control rovers, robotic arms, or even machineries with the swing of one hand. They are working on including this technology in spacesuits, which could have fascinating implications for future missions to the Moon and even Mars. This would allow astronauts to stay safe inside bases while the machines are doing the job on the field. It's exciting to see different hurdles being overcome in the mission to find and gather lunar water. But while there are successes, there are also failures. In July 2024, NASA announced that it was cancelling its Volatiles Investigating Polar Exploration Rover, or VIPER, which had been intended to be the first ever mission to explore the Moon's South Pole and search for water ice. The mission was intended for 2023, but due to delays in the rover's construction and a tightening NASA budget, VIPER got pushed back to 2025 and then was cancelled entirely. The rover, now already built, may be scrapped for spare parts. This is a big blow, as no other US project over the next few years is scheduled to have the same capabilities as VIPER, which was both mobile and capable of exploring the subsurface of the Moon, not just its surface, to see if water ice could be found there. Many scientists outside of NASA were surprised at the cancellation, with some calling it a dark day for lunar science. Hopefully, another space agency or company will step in to make use of the operational rover. Otherwise, it seems to me to be a terrible waste of time, money, and expertise. But NASA is not the only space agency finding lunar exploration challenging. 5 of the previous 9 moon landing attempts have failed. But even if they had succeeded, perhaps they would have been surprised. As it turns out, lunar water, that precious resource vital for the establishment of any human colony on the moon, is proving oddly difficult to actually locate. We have repeatedly detected it in spectroscopy readings, and yet, when we take a closer look at where it ought to be, instead, a mystery appears. The established belief among scientists today is that the permanently shadowed regions of the moon are one of the most likely places to find frozen water ice. But because it's so dark down in these craters, it's difficult to know for sure exactly which craters house what. It would be unfortunate to build a scientific base, only to discover that the crater next to you was completely empty. Sadly, LRO, the NASA lunar orbiter tasked with mapping out the entire surface of the moon, has its limitations. Its onboard camera, the LROC, is not capable of piercing this darkness. But there is a new camera circling the moon that can. The reason why I said earlier that 6 countries had sent probes to the moon before December 2022 is that on the 16th of December, that number actually rose to 7. After a 4.5-month journey, South Korea's Danuri probe arrived in lunar orbit, and Danuri's discoveries provided even more insight into lunar water, as well as raising further mysteries. NASA has actually been working closely with South Korea on Danuri, providing them with scientific expertise and communications and navigation support in a spirit of mutual international scientific collaboration. In thanks, South Korea's KARI space program gave NASA 7 kilograms of space on their Korea Pathfinder lunar orbiter, or Danuri as it's locally known. A composite word made from dal, which means moon, and nurida, which means enjoy. NASA considered what scientific instrument could be best placed on Danuri, and in the end they went with a device known as ShadowCam, a younger sibling of LRO's own narrow-angle camera, with one notable enhancement. Thanks to its 200 times sensitivity, it turns images like this into images like this. This incredibly clear image is of Shackleton Crater, found at the moon's south pole, the first ever site photographed by LRO. And now, thanks to Danuri and ShadowCam, we can properly peer into its inner basin. It turns out that Shackleton does not look that different from many of the other craters on the moon. Its cratered floor is covered in bumpy hummocks. But strangely, there is no obvious ice here. Perhaps this is because Shackleton is a smaller crater, meaning that the temperatures within do not drop quite so low as would be needed for ice to reliably form. One point of interest is the clear trail left by a boulder as it rolled down the crater side, visible near the top of the image. Such tracks are common on the moon, as the lack of wind means that any disturbance of the dusty ground is never covered up again. This track could be extremely old. I said that perhaps the reason no ice was found in Shackleton was because Shackleton was a small crater, but ShadowCam has now peered into many different craters in both the North and South Pole regions, and as of yet, its discoveries have only deepened the mystery of lunar water. In spite of Chandrayaan-1's findings all those years ago, none of ShadowCam's captured images showed the telltale glint of water ice, either in glaciers or as a light smattering of frost. And it only gets stranger when we consider one of the findings of India's Chandrayaan-3 mission. It was Chandrayaan-1 that first detected evidence of water on the moon's surface, But Chandrayaan-3 would take an even closer look, only for its findings to come back quite different from what scientists had expected to see. India's Chandrayaan-3 moon mission had already proven historic. It put India in the history books for being the 4th nation to ever successfully land a spacecraft on the moon, and the very first to ever land at its south pole. Sorry, Viper. The lander Vikram and the rover Pragyan already made discoveries that could profoundly impact our understanding of the moon's chemical composition and geological history, and has given the world vital data that will aid future return missions to our lunar neighbour. And yet, for all the praise, which is well deserved, it's what Chandrayaan-3 did not discover, but should have, that I find the most intriguing. Have you noticed it too? India's NASA equivalent, ISRO, the Indian Space Research Organisation, made press releases before the launch, and there was always one thing they claimed they were primarily there to find. One reason the South Pole was picked out over all other locations. One mystery about the moon that is deepening the more we investigate, and yet needs to be solved before we can expect to start setting up permanent bases up there. Simply put, where is all the water? Chandrayaan-3 was launched on the 14th of July 2023. It was made up of a lander module called Vikram, a small rover called Pragyan, and an orbiter module that carried the other 2 components across the Gulf of Space. On the 23rd of August, Vikram, with the little Pragyan tucked inside, touched down on the moon's surface at the beginning of a lunar day. But time was not on their side. Chandrayaan-3 was a surprisingly cost-effective mission. While NASA's Artemis mission launches will each cost on average $4.1 billion, the entire Chandrayaan-3 mission only came to 6.15 billion rupees, or about $75 million, ironically less than what many modern blockbuster space films take to produce. Perhaps Hollywood should consider filming their next moon film on site. However, with this lower budget came technological limitations. When the lunar night fell, Vikram and Pragyan would be subjected to temperatures of minus 120 degrees Celsius, temperatures they were not designed to survive. A lunar day lasts 14 Earth days. The Chandrayaan-3 mission would need to complete its major objectives in that time, as their odds of surviving to the day after that were slim. And so Vikram lowered its ramp, and Pragyan, the rover, powered up and headed out down onto the moon's surface. Pragyan is a 27 kilogram, 6-wheeled rover that came equipped with an alpha particle X-ray spectrometer for analyzing the chemical composition of the moon by firing radiation at it and seeing what wavelengths bounce back, and a laser-induced breakdown spectroscopy instrument that does a similar thing, but this time by firing a laser at the target of interest and analyzing the light wavelengths that are released by the resulting plasma. These 2 tools together would be enough for Pragyan to attempt to find water or any other interesting substances, confirming their composition for scientists once and for all. And so it set to work, deploying both instruments on the ground next to it. Within days, the results started to come in. Aluminium, calcium, iron, chromium, and titanium were all found on the moon's surface, along with other interesting elements like oxygen. Indian scientists were most excited at the first ever in situ measurement of sulfur at the moon's pole. Sulfur is an exciting element to find, as it helps us understand the evolution of the moon over time, and indicates there used to be volcanic activity in the region. But in spite of all these discoveries, there was one element that was not showing up in the analysis. The all-important hydrogen was notably absent. Pragyan set off to explore further afield. Guiding the rover was all done manually by scientists back on Earth, looking through Pragyan's onboard navigation camera. This had to be carefully done, as the signal delay between Earth and the moon meant that orders for the rover to halt lagged by a little under 3 seconds, time that might make all the difference if the little 6-wheeled rover was to avoid overturning. And indeed, this nearly happened. Early on in Pragyan's journey, the rover had to speedily stop to avoid falling into a large 4-meter crater scientists hadn't initially realized was there. I say speedily. Pragyan's move speed was 1 centimeter per second, hardly the fastest of sprinters. Over the course of its 2-week life, Pragyan traveled no more than 100 meters from Vikram. Fortunately, the crater was detected in time, and scientists were able to turn around and choose another route. However, when you look at Pragyan's route, you notice that there was a second moment where Pragyan did not travel down into a crater it came across, instead electing to go around. No photos of this second crater are currently available, so we are left to conclude that no ice was spotted there. Vikram itself did not remain idle during this time. It performed temperature readings of the moon's surface, digging 10 centimeters deep to measure the moon's warmth at different depths. It measured the plasma content of the atmosphere. Good news, there's not much up there, so radio communication to the moon likely won't get much interference. It detected a possible moonquake, which, given the small 2-week window, was some excellent timing. At the very end of its journey, in a moment of final enthusiasm, the Vikram lander even successfully performed a 40 centimeter high hop, firing its boosters to lift itself off the ground, moving 30 to 40 centimeters along from its previous destination. Indian scientists had wanted to test how easy it would be for future landers to one day propel themselves back into orbit from the moon, and this was a useful practice run. But none of this helped the Chandrayaan-3 mission to find water ice. By the 4th of September, time was up. Vikram and Pragyan were ordered to power down. ISRO scientists had hoped to wake them up again once the night ended, but this hope proved to be fruitless. The 2 lunar explorers had communicated with Earth for the last time. ISRO and the scientific community at large lauded their efforts and called the mission a success, and indeed it was, as India had gained first-hand data from the moon that would be extremely helpful in building a picture of conditions at its poles, along with furthering our understanding of the moon's history. However, it definitely raises a mystery. When I first heard that water ice had been detected on the moon, I envisioned in my mind frozen ice lakes, or possibly tall penitentes. Perhaps a light frost, as vapor from the moon's atmosphere ended up trapped in these darkened craters, freezing over the surface and building up over time. We know from orbiters like Chandrayaan-1 that water ice is indeed in these craters, and yet Chandrayaan-3 has joined other missions in failing to actually see this ice for themselves. Given that Pragyan's analysis of the lunar regolith revealed no signs of water molecules, where is the water ice that Chandrayaan-1 detected? While this mystery is confusing, Chandrayaan-3 offers us a possible answer. Not through Pragyan's explorations, it's actually Vikram that possibly hinted at the solution. When Vikram used its chased temperature sensor, it was able to take 10 different readings of the moon's temperature, starting at the surface and working its way down in 1 centimeter increments. What it found in the space above the moon's surface was a temperature a little under 60 degrees Celsius. Definitely too hot for you to walk around in if you happen to be on the moon and somehow didn't care about the lack of air. But curiously, as Chase measured deeper and deeper beneath the surface, this sweltering temperature dropped off fast. By 8 centimeters deep, the new temperature Vikram was detecting was minus 10 degrees Celsius. That's a big drop. From this we can see that lunar regolith is a really poor heat conductor. But that also indicates quite clearly that the best place we're likely to see ice is not resting on the moon's surface, but we actually need to look beneath it. There's much we don't understand about the moon and its water cycles. There's growing evidence that the moon contains quite a lot of water, and yet extracting it will take understanding where that water can be found, and how it moves throughout the long lunar days and nights. Is it affected by solar radiation? Is it trapped in hidden deposits? Although Chandrayaan-3 only lasted 2 weeks, which I'm sure is less time than ISRO scientists would have liked, it has offered us vital insights into the conditions on the moon. As far as water is concerned, at the very least, it has given future astronauts this one piece of advice. If you want to find a drink of water on the moon, you might want to start by bringing a shovel. There have been a lot of awesome images in the Astrum videos over the years. Sometimes the visuals we show in our videos are so colourful, so grand and so awe-inspiring that the short 3-second clip doesn't really do them justice. In those cases, I felt it would be really cool if there was a way to come back to these images again and again, to relive the magic of those moments and to capture the power and enormity of space. To that end, I've spent the last couple of months working with artists to develop 70 by 50 centimeter posters that captures those epic moments. We've created a set of premium prints that look great and act as a daily reminder of the universe that surrounds us. Perfect for bringing grandeur to your wall or as an inspiring motif in your office space. Right now, they're available at a special early bird price in the run-up to Christmas. Follow the link electrify.art/Astrum to check them out, and do let me know what you think of them actually in the comments below. Thanks for watching, and thanks to our crew of Astromnauts over at Patreon who help us make science knowledge freely available to everyone. Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you haven't already, but you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.